Alright guys, let's discuss this problem. This is the last problem from the chapter on work and energy in IIt Verma. The problem says a smooth sphere of radius r is made to translate in a straight line with a constant acceleration a. Particle kept on the top of the sphere is released from there at zero velocity with respect to the sphere. Find the speed of the particle with respect to the sphere as a function of the angle theta it slides. Of course, this sort of becomes an easy problem if there were no acceleration in the sphere itself, right? But of course, the sphere does move with a constant acceleration in this direction. So the way to approach this problem is to use the work energy theorem in a non-Newtonian frame of reference, right? So we attach the frame of reference to the sphere itself, which is moving at an acceleration a. So how that would work is like so. So we have this non-Newtonian frame of reference moving with an acceleration of a. Of course, if there is a mass m in this frame of reference, it experiences a zero force in the direction that's opposite to the acceleration of the frame of reference, and that's a minus ma vector. So let's write down the work energy theorem for the non-Newtonian frame of reference. So we have work of the non-conservative force plus the work of the zero force is equal to change in the mechanical energy of the system, right? And of course, there's no non-conservative force in setup, so that zero works out to zero. But for the work of the zero force itself, we have, so how much distance has this thing moved, right? So if you see, the particle has moved this distance. So in the direction of the zero force, that is this direction, the particle has moved up the value of r sine theta, right? So therefore, the work by the zero force itself in the direction that the zero force acts is WPS is equal to FPS multiplied by r sine theta, right? Of course, that would be MA r sine theta. Now note, of course, that because the MA force acts, the zero force acts towards the left, and the movement of the particle is also towards the left. When you multiply both these quantities, we arrive at a positive work done by the zero force. So that's important to note. So then, what about the right side of this equation? So we have EA and EB. So we have EA is equal to half mv square. Of course, at the initial position, when the particle is at the top of the sphere, the velocity is zero, right? Plus, now, of course, we have to define the potential at some point. So with respect to which we then calculate the potential, the gravitational potential, right? So let's assume that at the position, that's the middle of the sphere, the potential energy, the gravitational potential is zero, so U zero. So therefore, the potential energy, the gravitational potential energy at the point A would be U is equal to mgr, right? So we have mgr for the potential energy at point A. Similarly, we have EB is equal to half mv square plus mg. That would be, of course, r cos theta, right? So you can see this is r cos theta. Okay, so let's now equate the left and right side. So we have WPS, the work of the zero force, that's MAR sine theta, is equal to EB minus EA, that's the final mechanical energy minus the initial mechanical energy. Then that would be half mv square plus mg r cos theta minus the initial mechanical energy. That would of course be mgr because initial velocity is zero. So therefore we have to rearrange the terms and bring v on one side. We would have, so we have v is equal to 2. Now let's take r from this whole thing outside. A sine theta minus g cos theta minus 1 under root of that. Okay, and that's our answer.